Hi, my name is Colby Snyder, and I spent this past summer studying how we can use advanced coating materials to address the urban heat island effect. The urban heat island effect is when cities get much hotter than their surrounding environments. And I'll explain three of the most important. So, first, low albedo or low reflectance materials absorb solar radiation, and this causes them to heat up faster than the areas surrounding a city. And then once the buildings heat up, they would emit that heat as infrared radiation, but it can get blocked by air pollution or buildings, causing the heat to stay trapped in the city. And then similarly, with simply more mass in the city, there's more heat that can be stored. And this means that the cities take longer to cool off. So even after the sun goes down, cities can stay at dangerously high temperatures for several hours. And it's really important to address this issue because as the world heats up, more people are moving into cities. The UN project that by 2050, 68% of the world is going to live in urban areas. And that's more than a 20% increase from right now. And the figure is even more dramatic for the US, where 80% of people already live in areas that can be classified as urban. And that's expected to increase to 89%. So the majority of the world is going to be living in the most vulnerable areas to heat. And one of the biggest factors in this are roofing materials. So this image is an example of asphalt roofing tiles that are one of the most common roofing materials in the US and in Philadelphia, especially on residential buildings. And dark colored materials like this can easily get up to 50 or 70 degrees Celsius. And that can heat up houses and the surrounding cities to intolerable temperatures. So it's really important to replace materials like these with other cooler alternatives. This map from the Philadelphia Heat Vulnerability Index shows how much of an issue extreme heat is in our city of Philadelphia. So the lighter yellow colored areas are the least vulnerable, and then the dark red areas are the areas of highest vulnerability. And you can see how they're concentrated in North and West Philadelphia, where like older housing materials are typically more vulnerable to heat. And one of the major differences is the types of roofs used in these areas. And this can be seen by comparing a neighborhood from the most vulnerable region to one from the least vulnerable. So, for example, Hunting Park, which is one of the most heat vulnerable neighborhoods in the city, versus Fairmount, which is one of the least vulnerable. You can see visually in these images from Google Earth how like just the sheer difference in roofing materials. So in Hunting Park, it's largely dark colored roofs with some light roofs interspersed. And then Fairmount, by contrast, is almost exclusively white, cooler roofs. And this means Fairmount's a much safer place to be as temperatures climb in the summer. And concerningly, it's actually a lot more expensive to live in these less heat vulnerable neighborhoods. So Hunting Park, where the heat vulnerability rating is very high, has 47% of its population below the federal poverty line, as compared to just 6% in Fairmount. And then similarly, the median home value in Fairmount is almost 6 times that of Hunting Park. So it's really important that we come up with cost-effective solutions to address these inequities. The first part of my project this summer was looking at the existing approaches to cool roof coatings. So I started with commercial approaches that are already extensively used. And the first one is cool paints, which try to optimize the amount of light reflected and then also the amount of thermal energy that can be emitted from the surface. And this image shows how more recently colored paints have been developed, like the gray one on this roof that can still be classified as cool. And that's because almost 50% of the inbound solar radiation is in the infrared spectrum. So by using IR reflective pigments, you can afford to not reflect the entire visible spectrum, producing a like color, and then you're still reflecting the majority of incident solar energy. And then the next approach that's been used is spray coatings like this spray polyurethane foam. And that combines the reflectivity of cool paints with um, insulation. The porosity of the spray foam coating provides like an insulating barrier between the hot outside and then the air conditioned interior, which can save more energy. And then a third approach are green roofs like Sear Green in Philadelphia. And these have a multitude of benefits. In addition to leveraging natural evaporative cooling, they can purify the air, and they're what's known as an inverted roof design, meaning the waterproof membrane is on the bottom of the roof. And this protects it from the elements, especially UV light, and in theory allows it to last a lot longer. Each of these approaches, though, is limited by its cost, and it's important that we can develop materials that are even more cost effective so they can be deployed in the most heat vulnerable areas. Next, I looked at the current materials that are being explored in labs across the world, and one of them is still passive radiative cooling, the approach that's used in the paint from the last slide. And researchers are seeking to further optimize the amount of light that can be reflected, and then also the amount of longer wavelength IR heat emitted through the infrared atmospheric window. And the first approaches to this used reflective pigments like titanium dioxide. And more recently, a subclass of porous materials have emerged that substitute microscopic air voids for those pigments that have a similar light scattering effect without having any physical pigment present. And these have achieved really impressive results recently. And then another class of materials are phase change materials, which work by alternating between the solid and liquid phase in like a day-night cycle. So as the roof heats up during the daytime, it absorbs that energy and melts or transitions to the liquid phase. And then when temperatures drop again, it's able to emit that energy, return to the solid phase, and be prepared to do the same thing the following day. And a similar principle has been used in evaporative cooling roofs, which typically use a hydrogel to absorb moisture overnight and then evaporate it during the daytime in the solar heat. And each of these have shown really impressive thermal results by converting the sunlight into latent heat instead of sensible heat, but they're limited by their durability. A lot of the phase change materials change their volume during the phase transition, which could put a lot of stress on surrounding materials, like you see in this diagram. And then also some of them are less durable and couldn't even be walked on, which really limits their use cases. This summer, we also had the opportunity to visit the Dow Chemical Company's Springhouse farm. Dr. Heather Eckenrode showed us how they conduct accelerated weathering tests of all sorts of different coatings, including cool roof coatings. And it was really cool to learn how important durability is for coatings, because in addition to making a high performance coating, it has to be able to withstand infrared radiation, not infrared, ultraviolet radiation, and other things like thermal expansion and contraction of the substrate and moisture from precipitation or condensation. And this is actually a big problem with a lot of existing coatings. The Cool Roofs Rating Council studied thousands of different coatings and measured their solar reflectance index, which is a composite value of a material's reflectance and emittance. And they found that after just 3 years, a lot of coatings SRI decreased by over 50% and more than 100 decreased by over 25%. So it's really important that like our highest performing materials are able to maintain their SRI for many years so we can have cost-effective solutions that don't need to be replaced year after year. And then the next step in my summer project was developing an apparatus that we could use to test our own coatings that we'll eventually make in-house. the goal with this was to make an enclosure that could simulate the conditions inside a real house as it's exposed to sunlight. And we did this with the 3D printed box that you see in the middle. So this is made of ASA plastic in white because ASA has a relatively high glass transition temperature, 85 degrees Celsius, which is enough for our purposes. And then the white color is so we can hopefully isolate the effect of different roof coatings and reflect most of the light that actually hits the box. And then for the roof, we used this aluminum substrate that you see on the left. And these are nice for two reasons. First, they offer us a standard substrate so we know that everything is controlled trial to trial. And second, they simulate real world conditions because metal roofing is used in a lot of different places around the world, especially temporary housing like refugee camps. And some of these places are in the most heat vulnerable areas on the planet. And it's important that we can develop coatings that are able to adhere well to metal surfaces in addition to more common roof materials in the US. And then once I had this apparatus ready, I used an Arduino microcontroller to program 3 different temperature sensors that I use to monitor the box. So the top temperature sensor, which is the metal probe, attaches directly to the metal substrate to measure its temperature. And then the 2 white temperature and humidity sensors go inside the box at the bottom and outside the box. So I can contrast the air temperature inside the enclosure with the air temperature outside the ambient conditions. And when I had the sensors in this configuration, I did a quick test, which you can see in this plot just as a proof of concept. And this shows how the Arduino can log data over a given period of time. So the orange line is the temperature of the roof, or the sensor that will be used to measure the roof temperature. The blue line is the interior temperature of the enclosure, and the green line is the ambient temperature. And then after I confirmed that the sensors were working, I did an initial test outside using an uncoated aluminum substrate. And I learned a few more things from this. First, error 1 shows a sudden drop in roof and ambient temperature. And that was because a cloud passed overhead. And it was cool to see how profound of an effect that could have. I didn't expect that it would affect the roof temperature that dramatically, that quickly, but it's good to know. And moving forward, we'll carefully monitor the weather so we can get results that can be compared day to day. And then the second arrow, which shows the ambient temperature dropping from 41 degrees Celsius to 34 degrees Celsius, was because I realized halfway through that there was a big problem with this setup. And it's depicted on the left. The ambient temperature sensor is sitting on the table, and it's actually measuring the temperature of the table, which was heating up from the sun. So by moving it off the table and suspending it in midair, I was able to get a better reading. But it was still 34, 35 degrees Celsius, which isn't exactly accurate. And that was because it was still in the sunlight. So for the next test, I moved it into the shade to hopefully get a better reading. This picture shows where it was in the next test, and it did make the readings a lot closer to what the weather was showing. And the main change I made for this test was coating the aluminum substrate with black PVC tape to get a baseline value. And after just 20 minutes, the roof heated up to 50 degrees Celsius, and the inside of the interior of the box heated up to 38 degrees Celsius or 100 degrees Fahrenheit pretty shortly afterwards. So after that, I swapped out the black roof for a white one to see what the difference would be. And it was very dramatic. So I used a white Teflon coating instead of the black PVC coating, and the roof only reached 38 degrees Celsius. So it was about 8 degrees over the ambient temperature. And that's more than a 50% reduction from the 20-degree difference for the black roof. One weird feature of this graph is that the internal temperature and the roof temperature are about the same the entire time, which really isn't what I expected. And I think that it's because there was a lot of heat being conducted, again, from the table into the model house. So that's another issue that we can correct moving forward. But I thought it was really interesting just to see how these two initial tests showed the stark difference you can get from a really simple switch in roofing materials. So this fall, I'm going to continue working on the Cool Roofs project. And my first step will be to perfect the experimental apparatus. And a few steps I want to take are elevating the model house so it doesn't contact anything on the ground, which is something that's been done in past papers. And I'd also like to eventually 3D print a few more model houses so that we can test different roof coating materials in parallel. And that would let us like truly control the environmental conditions. And then once we have the experimental setup pretty solid, we'll select different materials to test. And I'd like to start with different high performing materials from the literature because while a lot of people have used similar setups in the past to test their own materials, there aren't very many studies that compare different materials using the same for a comparison. So this would be a good way to sort of work out all the kinks with our setup while also filling a gap in the literature and providing a fair comparison of different materials. And then a final thing we want to do are citizen science efforts to monitor extreme heat in Philly, which is something that's already being done at some of our neighboring institutions. And for this, we'd work with actual residents of Philly neighborhoods to collect heat data on their areas. And that way we can get real-time information on how the heat situation is evolving in our city. So I'd like to thank all these people who helped me this summer. It wouldn't have been possible without all their support and ideas. And thank you all for listening.